Okay. Well, so thanks for coming to this afternoon session. Thanks also to the organizers, if they're here. Okay. So this is the TA session for STAS course. And I will basically speak about two things I've prepared. And I will also speak about the things you might ask me to speak about. So I'll speak about two things. I'll speak first about the Ising model, and then I'll say a few words about discrete harmonic functions that will allow you to cross the i's and dot the t's, or the converse, for the UST proof of Riemann's mapping theorem. Okay, so about the Ising model, just remind you the definition, at least to set the notation. So you're given a graph G with the vertices V and edges E, and the probability of a spin configuration sigma in the probability space, which is just the space of random assignment of spins to the vertices of the graph, is proportional to exponential of beta times the sum. Maybe I should write a bit bigger. Over all the adjacent edge vertices of the graph of the product of the spins at the endpoints of the edges. Okay. So what I want to say about the Ising model. So first, let me remind you that in the case of Z2, which we will dealing most with, we will consider the critical value of beta, which is equal to 1/2 of log of square root of 2 plus 1. So it's important for computations, but the Ising model is conjectured and actually proven in many cases to be universal in the scaling limit at criticality, meaning that if you consider the Ising model on the triangular lattice, this critical value of beta would change, but what you would see at the critical temperature in the scaling limit would be the same, qualitatively at least. Okay, so what I have to tell you about the Ising model, I want first to say something about the FK model and the Edwards-Sokal coupling, which was explained to you yesterday by Stas and mentioned by Pierre. So what the FK model is, I remind you, it's a model defined. It's a percolation. It's an edge percolation model, bond percolation model. So the configurations you're considering are just this shape, and the probability of an edge configuration is proportional to p to the number of edges of omega 1 minus p to the number of edges that are not there, and q to the number of clusters of omega. So I think I don't need to draw a picture, but just something which is important, the number of clusters. So you count the number of clusters of vertices. So if you have an isolated vertex, it counts as one cluster. You should not forget that. I think it's important. Okay. So what's the link between the FK model and the Ising model? Actually, the FK model was introduced as a tool to study the Ising model. The link is the following. So this Q models the number of states of your model. So in our case, we will take Q equals 2. So the proof I will do work also for Potts model. So I will always do them for the Ising model. So the correspondence between the Ising model at the temperature beta, and this works for any graph, is the following. You take p to be 1 minus exponential of minus 2 beta. Okay. So you've heard yesterday that there is a coupling between the Ising model and the FK model. I would like to take a point of view which is maybe a bit different, although it's in the end the same, which is just explain how from an FK configuration you can get an Ising configuration and conversely. So. I'll then comment a bit on that and explain what it tells you already on the Ising model. So it's very simple. The answer to this question is just toss a coin for each cluster, a fair coin. And set the spins on the vertices of that cluster to plus or minus 1 according to the coin. So it's very simple. You have an FK configuration, so it's a percolation configuration. You have edges and the link vertices. For each of the clusters formed by these edges, you toss a coin, and if it's heads, you put +1 on all the vertices of that cluster, and otherwise you put -1 on all the vertices of that cluster. So, so it's very simple. Why is it true? So what you should do is just look at what is the probability to get a given spin configuration with this procedure, and just check you get actually the Ising model Ising model probability measure. So let me just fix a bit of notation for a spin configuration sigma. I'll denote by gamma of sigma the set of edges of the graph such that the product, the two spins at the endpoints of this edge are the same. Okay? So the FK Ising coupling is a coupling between model on sides, which are the spins, and on the edges, which is the percolation model. And so for each spin configuration, I just fix the set of edges where, at the endpoints of which the spins are the same. And so let's fix a sigma, a configuration sigma, and look at the probability to get sigma with this procedure. So, so probability to get sigma with the procedure star is simply what? Is simply the sum over all the FK configurations of the probability of getting the FK configuration times the probability that this FK configuration leads you by procedure sigma by procedure star to sigma. Okay? So it's very simple. So it's what can you say a priori? So for a spin configuration, what you know is that if you have different spins, they are in different clusters, FK clusters, right? Because if they were in the same FK cluster, by this procedure, you would get the same spins. So actually what you notice almost immediately is that you should sum of the only contributions that give non-zero the only edge configuration that give a non-zero probability here are the ones where this omega is included in gamma of sigma. So let me write what we have. So it's p to the omega 1 minus p to the number of edges minus omega times 2 to the number of clusters. Okay? And what can you do now? Well, two things. First, so this is the probability of the spin configuration. First, now, given such a guy, what is the probability that you get exactly what you want? So how many choices do you have in this procedure star? For each cluster, you have one choice. You have to toss 1 point. So the probability to get exactly the spin configuration sigma you have fixed and you want is just 1/2 to the number of clusters. Because for each of the clusters, you should get the right thing, and you have a number of cluster choices. Okay? So this simplifies. And what you get is, so you can you can factor out a number of 1 minus p. Why is it so? Because I told you this is just the edges that are not in omega. But the edges that are not in omega, they're not in gamma either. So we can take out all the edges that are not in gamma. And what I get is sum over all the edges in gamma of sigma of p to the number of edges of omega times 1 minus p times the edges that I haven't counted there, which are the edges of gamma, the number of edges of gamma minus the number of edges of omega. Okay. So here, you maybe recognize the partition function of the collation model, which is not very interesting, which is equal to 1. So this is equal to 1. And I told you p should be equal to 1 minus e minus 2 beta, and what you get is just e to the minus 2 beta, number of edges, minus gamma sigma. And this is exactly the definition that Stas used for defining the Ising model in the first course. Probability of a spin configuration is proportional to that. It's quite easy to check from the definition that you get exactly what you want. So in this way, it's easy. In the other way, it's easy too. So just to tell you what the procedure is. So to obtain an FK configuration from an Ising configuration, what you do is for all the edges, so from an Ising configuration sigma, say, of gamma of sigma, sorry. All the edges where the adjacent spins at the endpoints of this edge are the same. Put them each with probability p independently. So what you do is you perform a percolation of parameter p on the cluster, on all the edges that are in this gamma of sigma, and you get an FK configuration. Was it so? Proof is easy also. So you fix you fix an edge configuration omega, and you look at the same thing, the probability to get omega from an Ising sample where I have added these edges. And so probability to get omega is the sum over all the spin configurations of, same as before. I'll just write this because it's make things proportional. Exponential of beta sum over all the edges, sigma x, sigma y, of what's the probability now. So you should, it's a percolation, as I told you, on gamma of sigma. So it's what do I do? Wait. So this is the probability of a spin configuration. And for this spin configuration, what is the probability that I get the right thing? So for each of the edge, I know whether I want it in omega or not. So what do I have? I have just p to the number of edges of omega times 1 minus p, the number of edges that are not in omega but were in sigma. Okay? And what? So now I should do the same. I should look at all the spin configurations that that give me some positive probability. What are those? Those are the following. You should have this relation. Why? Because if you want an edge in your FK configuration, with this algorithm, you must have the two spins at the end points of this edge that are the same, because otherwise you have no chance of getting that edge. So I can rewrite that as a sum over all the sigma such that gamma of sigma contains omega. And okay, have the same. And now what do I do? Again, I should just factor out. So sorry, there was a 2 to the number of clusters. No, sorry, it's fine. Okay, so now I should just factor out something and see that I get exactly what I want. So this exponential, I will rewrite it in the following way. Product over all the edges of e to the beta sigma x sigma y. And this I will replace by the definition. So it's, no, this I won't replace the definition. I just write it this way. P to the number of, okay, just rewrite this. And this I just put in this way. No, wait, 1 second. Okay, so just p to the number of edges of, oh, okay, I'll just rewrite that. So I think it's simple from now. I should just look at all the edges that I'm guaranteed here. So wait. So okay, I should just replace this. This is just e to the minus 2 beta to the number of sigma, and this is just 1 minus 2 beta omega. And you see, I have a cancellation already. the thing is, I should rewrite this in this way. Exponential of beta to the number of edges of sigma. Why so? Because simply, okay, let me just. Should just say some word. Probability that of a spin configuration can be rewritten as exponential of product over all the edges of sigma of exponential of beta times them. So just something like that. So I should just use this thing here, and what I get in the end is something that simplifies, and I get probability of the number of edges of probability of the number of edges of omega times 1 minus p number of edges of e minus the number of edges of omega. Sorry, I'm a bit messy here. Let me just explain you. The thing is that it's just you need to be a bit further from the blackboard to see what's going on. But the thing is just that all the spin configuration will have the same contribution. And how many spin configurations do you have with this choice? You have 2 to the number of clusters of them. So I just write in words what I said. So all spin config, yeah. All spin configs, thanks, in the sum give the same contribution and they are 2 to the number gamma of sigma, to the number of clusters of omega of them. Why are there 2 to the number of clusters of omega of them? Because simply, if you have already your FK clusters fixed that you want, how many choices do I have to put the spin configuration? On each of the cluster, I should have all the spins the same. So for each of these cluster, I have 1 choice. So how many choices do I have? I have 2 to the number of clusters of them. It's just that. And to check you have exactly the same contribution for each of them. It's not difficult. It's just 1-line computation. But I'm not very used to do computations on Blackboard. So. OK, so now I'd like to talk a bit about boundary conditions. So what I've talked for now, we have talked about free boundary conditions. I don't put any information on the boundary. For conformal invariance purpose, I mean, what you study in the course, there are 3 kinds of boundary conditions: plus, minus, and free. Plus, minus, and free. These are the three boundary conditions that should be conformally invariant. The others are supposed either to renormalize to those or not to be conformally invariant. Okay. For the FK model, what boundary conditions have we seen? We have seen wired and free. So free is just what I explained. You don't put anything on the boundary. What Pierre explained yesterday, it was he explained that boundary conditions for FK it's a set of edges that you put together. So on the boundary of the graph, put together. So in Stas course and in conformal invariance, there are two kinds of boundary conditions for FK that are important. Those are the extremal ones, the wired ones and the free ones. So two important ones. Wired and free. So I explained you how to get an easing configuration from an FK class, from an FK configuration. You can get an easing configuration with plus boundary condition from an FK configuration with wired boundary conditions. So wired boundary condition for FK yield plus boundary condition for easing. Except, I mean, there's just one thing you should do. The cluster on the boundary, you should not toss a coin for it. You should just set it to plus. Okay? Okay, and one more thing I should say is that you can also consider mixed boundary conditions. This is the case where SLE takes place. So mixed boundary conditions are just combinations of those boundary conditions. So for instance, you can generate an easing configuration with plus boundary conditions here and free boundary conditions there using FK model. What you do is you sample an FK configuration with wired boundary condition on that arc. So you imagine you have a graph here and free boundary condition on that arc. And you just toss a coin for each of the clusters except for the one on the boundary that you set to +1. And then you get an FK configuration. So this is the setup of Stas course. So what I mean by that is that with Stas course, you understand FK model, but you also understand easing model with the mixed plus and free boundary conditions. How is it so? I told you basically is this. So what does Stas course explain us about this model? It will explain us that the interface that he defined in the course converges to SLE. But on more basic level, what you have seen yesterday already tells you something about the easing model. So easing interpretation of Stas observable. Who was the student of so what's the interpretation of this observable? So maybe you don't remember it, this observable. So let me just write what it is. So the observable of Stas is the following. you take the expectation of the indicator event that a point Z is on the interface, on this interface. So you fix a point Z and you look at when the point is in the interface. So if it were like that, it would just be the probability that Z is on the interface. But you have a complex thing, which is this winding number of gamma from B to Z. So it's a complexified version of the probability that an interface passes through the boundary point. So a priori, it has no clear interpretation in terms of the Ising model, since the procedure to get Ising clusters from the FK clusters does not seem to behave very well with this observable. However, still, you can say something when you evaluate the observable on the boundary. So when one evaluates the observable on the boundary, one looks at this quantity. And what can one say about this quantity? Actually, there is a very nice thing that happens, which is very, very easy to see, which is the following. The interface, gamma, has its complex phase, e to the minus I over 2 times this winding number, fixed on the boundary. So let me just put the points A, B, Z. When I'm here, when I have an interface that passes through a boundary point, it has no choice whatsoever on the winding number it does before reaching B. So when Z is on the boundary, this quantity is constant and depends just on the geometry of the boundary, but not on the particular realization that I take. So I can factor it out. And what I get is just probability that the point Z belongs to the interface. What's the interpretation of that in terms of Ising model? So on the boundary, F gives the probability that Z belongs to the interface gamma. Now, what can you say about the probability that a point is in the interface on the boundary? What it tells you is that there is a cluster, there is this cluster of plus spins that just arrives here. Otherwise, the interface would not go there. It's just because the point is on the boundary. So it actually, you actually have that this probability is the probability that Z belongs in the cluster of the upper arc. Okay, and what is the probability that Z belongs to the cluster of the upper arc in terms of FK model? It's actually expected value of the spin located at Z. So I'm a bit sketchy in the sense that Z was defined on the edges in the course, and now I take Z to be a vertex. But it's not a big problem, really. Why do you have that? Simply because of the following. I explained to you how to obtain an Ising configuration from an FK configuration. So how does it work? You toss coins. So if a point is in a cluster for which you toss a coin, its expected value is 0, because the coin is fair. While I told you that if the point is in the cluster of the upper arc, this boundary cluster, you don't toss a coin and you set it to +1, in which case the expectation is just 1. So you get that. So what it tells you is that the FK model actually represents geometrically how the influence of the Ising model spreads in the graph. You know, with this strategy, you can show, for instance, that probability that 2 points are in the same cluster is just equal to their correlations, to the correlation of the spins at this point. So, in general, for instance, probability, the expected value of the product of 2 spins is the probability that A is linked to B by an FK cluster. Because otherwise, if they are not even in the same FK cluster, you toss independent coin for the 2 clusters, and you get the zero correlation. If they are in the same FK cluster, you can toss a coin plus or minus 1. And in both cases, they will have the same sign. So the correlation will be 1. So as I told you, it explains how the FK model describes geometrically how the influence between spins spreads across the lattice. It tells you that if 2 spins are the same, it's partly by chance, and that can be viewed as they got in different FK clusters and you just tossed the same coin, and partly by the ferromagnetic influence. Okay. Okay. So that gives you a nice interpretation of stats observable in terms of spin correlation. What you have probably guessed is that we are going to prove convergence of stats observable to a function that he actually explained yesterday, is the square root of this conformal mapping to a strip, of the derivative of this conformal mapping to a strip. So what he tells you is that actually you're going to be able to compute exactly this probability in the scaling limit, for instance. And that's actually very useful for some applications. Okay. Yeah?
To do so, you need to go to convergence in the problem.
Right.
That's to explain only the convergence inside.
Right. Right. Okay, thanks. So yeah, you can prove accurately a convergence of this quantity renormalized appropriately only on a straight part of the boundary, or you can compare ratios of such quantities for different domains that share the same part of boundary. We won't explain that. It's just to give an idea of what you can do with stats observable as far as Ising model is concerned. Okay. Now I'd like to tell you a couple of things about other representation of the Ising model. So here you have seen a representation of the Ising model in terms of random cluster models that describe how this influence spreads up. Just one remark. Before that, what you see a priori from here is that it looks like the spin cluster, the clusters of the spins of the Ising model, are more ordered than the cluster of the FK model. The probability that 2 points are in the same spin cluster is bigger than the probability that they are in the same FK cluster, because they have already a chance of being in the same FK cluster, but it might more be that there is some, by flipping coins, if they are not in the same cluster, you can create a path between them. So it's a hint that Ising model is more ordered than FK model. And actually, it's true. And for instance, in the scaling limit, we cannot really prove that yet completely rigorously. But the FK clusters have dimension 15/8 in the scaling limit. You should give a precise meaning to that. And the Ising clusters have a bigger dimension. So it's 187/96. So you can see it's bigger. Okay, it was just a side remark, just tell you a bit what's going on there. Okay, now I'd like to pass to another representation, which is less straightforward in the sense it's not probabilistic, which I know better in the sense I will probably not screw up the computation, and which is very useful for understanding the scaling limit of the interfaces of the spin Ising model. So Stas, for now, his interest, he's now proving convergence of the FK interface between wired and dual wired clusters, as he explained, to SLE 16/3. But there is another problem, which is very interesting, and which was also solved by Dimachokak and him, which is the convergence of Ising interfaces of Ising spin clusters. So if you have a domain and you consider the critical Ising model with plus boundary condition on one arc and minus boundary condition on the other arc, the interface here, as he showed in the pictures on in the first course, converge to SLE 3. And the observable you use is, of course, not the same as for FK. And the representation I will explain a bit today now is a good motivation for the introduction of the observable you need to prove convergence of this. So as I told you, I will explain you some less straightforward representation of the Ising model, which comes under the name of Kramers-Vannier duality. It's not exactly the same thing as what Pierre explained yesterday. It's not a probabilistic coupling. It's the way to represent partition functions of the Ising model. So it sounds a bit magical the first time you see it, and even after a while, it still sounds magical. So the idea is the following, is to rewrite partition functions of models in other ways that have some statistical mechanics interpretations. Okay, so what is the and then you can do more advanced things with that, and you can, as I told you, get inspiration to prove convergence to SLE 3 of Ising interfaces. So very probabilistic things in the end. So what is the partition function of the Ising model? I was not interested in that up to now. It was just assumed to be there with this proportionality constant. It's what is the sum of all the Boltzmann weights of all the spin configurations. And the idea here, actually I'm not sure I will do the whole computation, but it's just, it's to rewrite this sum as another sum, and then to perform some Fubini, and then get a partition function of another model. So here I start with 3 boundary conditions. No, so nothing special. So I sum that, okay. And then I write this as a sum over configurations of a product over all the edges of the graph of exponential of beta sigma x sigma y. And let me just introduce a small notation for an edge E. Let me denote by sigma sub E the product of the spin sigma x and sigma y. It will just shorten a lot of the notation. So it's a sum over spins of product over edges. And now I will just write this as a hyperbolic cosine plus hyperbolic sine. Okay, and what do I do now? I just observe that this is plus or minus 1. So since the hyperbolic cosine is an even function, cos of plus or minus beta, this is just cos hyperbolic cosine of beta. And so there's a beta here, sorry. And here what I can notice is that hyperbolic sign is a not function, so I can put that in front. Okay, so what I get then, I put the hyperbolic cosine in factor. And then I get here 1, and here's hyperbolic sine over hyperbolic cosine. So this gets a hyperbolic tangent. So it sounds a bit weird a priori. Huh? So let me just rewrite what we have. I'll rewrite on the next blackboard. So sum of the sigmas of products of the edges of hyperbolic tangent of beta, hyperbolic cosine of beta, sorry. Beta times 1 plus sigma of E times hyperbolic tangent of beta. So this hyperbolic cosine, how many times does it come? Number of edges, so I can just put it in factor. And then what I do, I just expand this product. So for each edge, I have either 1 or this thing. So I just have 2 to the number of edges term, which can be easily indexed by the subset of the set of edges. I just count I just look at these contributions. So what I get is a sum over all these subset of edges of product over all the edges of this subset of sigma of E times hyperbolic tangent of beta. And this, I can factor out the hyperbolic tangent of beta here. And so what I get is same term, same sum of hyperbolic tangent of beta to the number of edges times the product of the spins. Okay. It sounds still a bit strange. Now I perform an exchange of sums. And this is really the point where you see something new appearing. You will see it's magical in the end. It's worth doing the computation, because now, so I have this sum of spins of this hyperbolic tangent, number of edges. So it was a cal E of the product of spins. The question is now, what are the contributions that give a non-zero? What are the subset of edges for which this sum is non-zero? Why would this sum be 0? Well, if, let me write what I'm saying. If E, a subset of the set of edges, is adjacent and it's not well written, a node times a node number of times to a vertex V, the sum over all the spins of the contribution is 0. Why is it so? If you have a vertex that belongs to a node number of edges here, what will happen? You're going to sum over all the spin configurations. So the thing is that this product will be a node function of the value of the spin here. You know, this is the product of the spins at the endpoints of the vertices of the edge. So if you have a vertex which has an odd degree in cal E, then half of the time he will come with plus, half of the time with minus, and the contributions will get different signs and hence cancel. Okay, so what remains are the spin configurations, the edge configurations, edge configs E such that every vertex has an even degree. And what are those? By Euler's theorem, these are just sets of loops. You know, if every vertex in a graph has even degree, it means you can create a well, it's just a set of loops that might touch at some points, but a set of loops that are sets of loops. And so what are graphically all the contributions? An edge configuration contributes to your sum if and only if it looks like that. So it's a collection of loops. Okay? And what is the weight of a collection of loops? So so what you do here, this term is now always 1. So it's just hyperbolic tangent of beta to the number of edges. Probability of an edge configuration E is just proportional to hyperbolic tangent of beta to the number of edges of E. But that's reminiscent of something. Stas, in his first lecture, he defined the Ising model precisely with such an expression, not the hyperbolic tangent, but just x to the number of edges of an edge configuration made of circuits. So what you have? Actually, what you have is that you have a collection of loops that can be interpreted as a collection of boundaries of spin clusters located on the faces of the graph. So let me make a picture. So what you have is that the following. You had your Ising models on the vertices of that graph. And now you have circuits on this graph, loops. It looks like there are spins on these faces. Okay? And actually, it turns out that here you have a new Ising model on the dual graph with you have a new Ising model on dual graph with a different temperature. Because before, it was the temperature before the beta temperature before gave rise to a factor which was exponential of -2 beta. Okay, so here you had one parameter, now you have another. It turns out that the critical point is the point precisely characterized by the fact that this is actually equal to that. It's the first way the critical temperature of the Ising was empirically determined. It was matching these two values. So what can you observe? We exchanged temperature. We exchanged what, actually? Temperature. Actually, you can check that if beta was smaller than beta critical, you exchanged it with a supercritical beta. So it exchanged low and high temperatures. And so the fixed point is the critical temperature. It exchanged the graphs. We exchanged the graphs. Because first we had an Ising model on the vertices, and now we have an Ising model on the faces. So it's a duality between graphs. And actually, it also exchanged the boundary conditions. what happened is that before, you had free boundary conditions. But if you trace the contours of spins with free boundary conditions, they are not made only of loops. The contours that are only made of loops are the contours of spin configuration with plus boundary condition. You know, if you have plus on the boundary, here, then it's easy to see that all the spin configurations in the bulk are in bijection with a set of loops. Okay? Well, you know, if I have things like that, I trace the boundary, I trace edges, a dual edge between different spins, and I get a set of loops. And conversely, if I have a set of loops, it's easy to recover the spin configuration. So actually, we started from free boundary conditions, and we ended with the graphical representation of of plus boundary conditions. So, well, it's a bit of magical trick that extends things. Why am I telling you about that? First, notice it's a bit similar in some sense to this FK thing, because in the FK model, you had this dual FK model where you put a dual edge to the edge that are not there. Like in percolation, you have clusters, you have dual clusters. And the dual of an FK model is get an FK model. And at the P critical, actually you get a critical FK configuration, a bit in the same spirit. What happens with boundary conditions? If the boundary is completely wired, the dual of the boundary is completely not wired, completely free. So it's a bit reminiscent to that. But this is, in sometimes, although it's less straightforward, it gives you crazier things. Because let me just make a comment on the computation I made. So I expanded this partition function. If now I want to compute a correlation of two spins, I put the spins here. Okay? Okay, it's not good letters, A, B. Well, you can go through all the computation, and everything carries on until the day here you end up with sigma A, sigma B. Still there. But now there is difference in the cancellations. I told you a spin configuration, an edge configuration will have its weight that cancel if unless every vertex has even degree. But now you have these additional contributions that make things reverse. The point A, each should have an odd degree in this configuration for it to have an even contribution here. And same for B. So what you get, if I do the same thing for Z of sigma B, say something like that, I get actually that you have loops, because every vertex has even degree, except the points A and B, which have odd degree. And that creates a path from A to B. Okay? Well, okay, so that's a spin correlation with free boundary conditions. What happens if I put the point A here and the point B here? Actually, I get the partition function of the Ising model with plus and minus boundary conditions. Actually, I get exactly the picture you would like to see appear when you study the Ising model, the interface between plus and minus spin clusters of the Ising model. So, dual interpretation. Partition function of Ising model with plus minus boundary conditions. Okay. So So that's nice. And actually, stats observable, I'm not going to spoil it today, but I can just tell you that it's precisely a complexified version of this spin-spin correlation that he uses. So it's precisely a sum like that with the complex weight here, taking into account a certain winding number precisely of this path that you should take to prove convergence to SV3. Okay? So that was a bit for the inspirational part. I'm just going to finish very briefly with these discrete harmonic functions, which have nothing to do. So you have questions for now? So just to explain you this coupling between FK model and Ising model, and this other representation, which is a bit fancier in some sense. In the sense, it's less straightforward. And you have questions? Okay. So let me just do it. There are two things I want to tell you. Discrete Harnack. What was it? It was the gradient. If you have a harmonic function f, a harmonic function f in a domain, and what you have is that the discrete gradient, so it's just a discrete difference, is at a point x is smaller than the max of the harmonic function divided by the distance of x to the boundary. So this is not easy in general to prove. I mean, for very general graphs. For the square lattice, it's quite easy. The idea is to use random walks. So you probably know that a harmonic function is solution to Dirichlet problem. And you probably know that solutions to Dirichlet problem can be expressed in terms of random walks. So a way to prove this is to prove the following lemma. Which Hugo told me. So it's just discrete Harnack it can be you can prove it easily. It follows from the following lemma. There exists, well, okay. Let me be more precise. Consider the two points on Z2, 0, 0, and 0, 1 in Z2. There exists a coupling of two simple random walk, and the first starting at 0, 0, and the second at 0, 1, starting one and 0, 0. Call them xn and yn, so that the probability such that the probability that they merge. So these are coalescent random walks, okay? That they merge before reaching distance d. D is smaller than an absolute constant over d. Okay? So why does it solve our problem? Because the discrete gradient is just the difference of the values of harmonic functions, function at two adjacent points. So what you do to compare the two values, you launch two random walks, and you know that the expected value of the function at the boundary of the domain of the value of the function at the point that you hit first on the boundary of the domain. Yeah?
Sure, it should be 0, 1.
0, 0, and 0, 1. Why?
Well, they can't merge by parity. Should be 1, 1.
No, they're simple random walks, really. They jump on. Yeah, no, I mean, okay, if you want to do a reflection on the real axis, you can't. But I'm not going to do that. No, it works. So you launch these two random walks, and solution of, you can write f is the expected value of f at x tau, where tau is the hitting time of the boundary. This is the solution of discrete Dirichlet problem, like solution to continuous with pronoun motion. So you launch these two random walks. So if they merge before reaching distance n, well, so since distance n is before the boundary, they will be together in the end, and they will give the same contribution. So, well, it's easy to check from that, from that lemma. So how do you construct this coupling? So two persons proposed me two different things. So Hugo proposed to do the following. So you do you launch a random walk here and say that this is 0, 0 and this is 0, 1. So you have the axis, the critical line 1/2, and what you do is you couple these two random walks in the following way. So you couple the two random walks so that one is the mirror image of the other. Say y is the mirror image of x, and whenever x hits the other side, you just make y jump to this thing and wait for one time, and then they go together. Another proposal. Okay. So what you should do now is estimate the probability that they merge. And what is merging in this case? It's just hitting a real axis before going to distance d. Okay? And so probability that not to hitting the real axis, this axis before getting to distance d, by Gambrell's rule estimate, you can easily show that it's 1/d in order. You can really have explicit bound. You can show that actually it's smaller than 1/16 of d. It's bigger than it's smaller than 1/16 of d. So probability 1 minus probability of that. Probability they merge, and probability they don't merge is smaller than 1/16 of d. I'll let you do this as an exercise. It's not very complicated. You would like in the end to get a comparison with a strip, and a strip it's a 1D problem, and it's just a Gambrell's rule estimate. Another way is maybe simpler. Is just to couple the two to couple the, okay, so it was 1, 0 in my picture. To couple the second coordinates to be the same, and just wait until the first coordinates get the same. And, well, here again, it's quite easy using Gambrell's rule estimate to get this estimate. So last thing is just the discrete building estimate, a weak version of that allows to treat problems of convergence of something to the boundary when the boundary conditions are nice. So in particular, it allows you to treat the problem of the UST. So a discrete building. So I will just put it in terms of random walks, and then you should interpret it correctly for solving the problem for the UST. So the probability. So if you have, so let R subset of Z2 be a discrete domain, be a connected graph. Now maybe I will just put it in terms of positive functions. So let Dima just have a suggestion how to formulate it nicely.
Well, it'd be harmonic layer of some part of the bond.
Okay, good. So, and sorry, and D1 be a part of the boundary of R. So let me make a picture just to explain what I'm going to do. I have a domain like that. And I have harmonic function which is equal to 1 on one side of the boundary. And I want to show that, and it's equal to 0 on the other part. And I want to show that the solution to the Dirichlet problem that with the 1 boundary value here and 0 boundary value there is nice close to the boundary in the sense that when you get close to the boundary, you converge quite fast to the boundary value, 0. So what you get for this function, so a part and to the other part. So you have a function g, solution to the Dirichlet problem. So it's just the harmonic measure of the upper arc. A solution to the Dirichlet problem with f on d1 equal to 1 and f on d2 equal to 0. What I want to say is that f tends to 0 quite fast when you get close to d2. So what then? There exists a constant c, which doesn't depend on the graph, which depends on z2 but not on r, such that g of z is smaller than c times distance of z to d2 to a power alpha. So there exists c and alpha, such that you have that. Okay, so the optimal constant, well, it's g? It's g, well, okay, it's g, not, sorry. Okay. You can leave it. Okay, yeah. Oops. So the optimal constant is just is 1/2. It's not easy to prove it, but getting that positive constant exists is not so difficult. The idea is that you launch a random walk to solve your problem, and you like to prove that the probability it goes far away without touching this part of the boundary is small. So what you can impose the random walk to do is whenever is to close circles, is to make circle turns, And for each of you divide the neighborhood of this part with 0 into analy. And in each of the analy, so they are concentric analy of sizes 2 to dk, say. And in each of these analy, the probability of closing a loop is positive. So the thing is that whenever you close a loop, you hit this part of the boundary, and then in expectation, and then you have a 0 contribution to the boundary. So to prove that the function, if the function wants to be bigger, it must have contributions where random walks go to there. So whenever you close a loop, you will hit the boundary. So you prove that at every scale, you have a positive probability of closing a loop. And in the end, what you have is that, well, the chance of never having closed the loop is not so big, and it's actually precisely this. So that's a sketchy proof, but quite easy to make rigorous of this inequality. So, okay, that's it. You have questions? Yeah? Okay, sure. So what you want to show is that, this function g is just the probability of hitting d2 before d1, d1 before d2. Okay. This is d1, and this is d2. Oops. So g of z is probability starting from z to hit d1 before d2. Okay? And so you like to show this probability is small. So we'd like to show that at every scale you have a good chance of hitting the d2. So divide the disk d z distance of z to d2 into concentric analy. Each twice bigger than the other. So you just have something like that. Small things. And in each of these analy, you have, so if you want to escape, you have to go through all these analy and not never hitting the boundary. So in each of these analy, you have a positive probability of closing a loop. The point is that, it was distance to d1, sorry. So the thing is that your enemy, d2, is here. This is d2. And if you close a loop at every scale, if you close a loop, whenever you close a loop, you will hit d2 after some scale. And the thing is that, so at every scale, you have a chance of failing. And in the end, all the scales just add up, and the chance never to have failed decreases geometrically in the probability of closing a loop. Okay? So my picture is not very good here. I will just do one more and finish here. So the thing is, look, you have this domain. You have d1 here, d2 here. You're starting close to d2. The thing is, you do concentric analy not as in the same previous picture, but like that. And the thing is, you run your work, and you don't want to touch here. You want to go there. So the thing is that if in any of these analy you close a loop, you hit this. Okay, right? If I go here and I close a loop, I hit this. The thing is that every such scale have positive chance of doing that. Because Brownian motion, or no, random walk just has positive chance of closing a loop. So so the thing is that you have log2 of dist of z to d1 over dist of z to d2 chances to fail, to hit d2 with probability say C prime, which is positive. So in the end, what you get, probability of escaping is smaller than C prime to the power number of to the power of log2 of this ratio of two distances. And so it's equal to precisely a certain so it's a certain constant. The dist is equal precisely to this ratio of distances to a certain constant alpha, and that's the proof. Okay. Other questions? Okay. Thank you.
You should say when the course starts.
So when does it start?